This video is the first in a series I will do on topics in chemistry. I want to start with the elements, the fundamentals of physical chemistry, acids and bases, and then chemical energy. I will eventually make videos on organic chemistry and biochemistry, all of which should lead into topics on molecular biology, where chemistry merges into biology, and the origins of life. Chemistry is a fundamental science like physics or biology. Chemistry is the intermediary between physics and biology. Chemistry overlies physics and underlies biology. At their margins, all three of these fundamental sciences overlap. Physics conforms to elegant mathematical formulas: F equals ma, E equals mc squared, and Maxwell's equations of electromagnetism, etc. Both chemistry and biology are a tangled web of mistily described phenomena that physics can only broadly outline, never mind explain or predict. Physics encompasses the study of the universe right down to subatomic particles, the very big and the very small. Chemistry occurs in medium-sized world, from the size of atoms to mountain-sized objects held together by chemical bonds. With a few exceptions, all the objects you see on Earth are held together by chemical bonds and are the result of chemical action. Life itself is chemically based, at least the parts of life that we can explain scientifically. There are some chemical phenomena that can be described precisely with mathematics, but most of chemistry is experimental. Most of the secrets of chemistry have been learned through observation and measurement. Chemistry is the study of substances. These substances are made of atoms. And for the most part, chemistry is the study of how these atoms interact to form molecules that in turn form compounds and mixtures. Chemistry encompasses a wide variety of interrelated subfields: inorganic chemistry, organic chemistry, physical chemistry, and biochemistry, all of which in turn have their own sub-branches. What all these chemistry subfields have in common is chemical bonding. That is, the interaction of atoms to bond with one another to form molecules. All of bonding involves a release or storage of energy. As in physics and most natural processes, chemistry tends to work in the direction of its lowest energy state. Chemistry and physics are deeply intertwined. One goal of physics may be to understand and predict why all these chemical bonds occur. But as of today, physics can only predict a very limited number of the outcomes of atom-to-atom interactions. Chemistry is such a broad science that it may forever remain separate and distinct from physics or any other science. The essence of chemistry is electrical charge. Chemistry is the study of the properties of substances and how they react with other substances. These substances are composed of atoms, and the molecules and compounds and mixtures of molecules that are composed of atoms. Chemistry is not concerned with the composition of atoms, except at a structural level. The composition of atoms lies within the topic of particle physics. Chemistry is only concerned with the most basic structures of atoms: protons, neutrons, and electrons, and the physics property called charge or electric charge, to distinguish it from other types of physics charges like color charge and magnetic charge that fall firmly under the science of physics. We don't know what charge is, we can only say what charge does. Charge is one of those fundamental properties of physics that we don't understand but take on faith. We use the effects of charge without understanding why it exists. Charge can be neutral, positive, or negative. Positive charges repel positive charges and attract negative charges. Negative charges repel negative charges and attract positive charges. The charge carriers for atoms are protons and electrons. In ordinary matter, one proton carries a charge of +1. One electron carries a charge of -1. When a proton is paired with an electron, their charges cancel exactly, and we say the charge on the pairing is neutral or zero. An object that contains equal numbers of electrons and protons is said to be electrically neutral, with the caveat that different regions of the object may be positively or negatively charged if the charge distribution is not homogeneous. Why electrons and protons contain exactly equal and opposite charges is a scientific mystery. It does not need to be so, except for our universe to exist as it does. A universe where opposing charges were not equal could not sustain chemistry or physics as we know them. A neutron has zero charge or is electrically neutral. In particle physics, a neutron can be created by forcing a proton-electron pair together. Likewise, a radioactive substance can emit beta rays or a stream of electrons if its neutrons are experiencing beta decay or transforming into protons by releasing electrons. It would be wrong to say a neutron is a pair of joined protons and electrons. A neutron is its own entity. Neutrons exist to allow the strong nuclear force to hold the nuclei of atoms together. Radioactivity and the strong nuclear force are topics of nuclear physics and outside the topic of mainstream chemistry. Mainstream chemists are usually only concerned with the mass that neutrons add to a substance. As an aside, the famous scientist Marie Curie was trained as both a physicist and a chemist. Marie Curie was the first woman to win a Nobel Prize and the first person to win a Nobel Prize twice. In 1903, Marie Curie was awarded the Nobel Prize in Physics, along with her husband Pierre Curie and Henry Becquerel for the discovery of radioactivity and their pioneering work in radioactivity. In 1911, Marie Curie won her second Nobel Prize in Chemistry for discovering the radioactive elements polonium and radium. Marie Curie named polonium for her native country of Poland. The 96th element curium, created in a nuclear reactor in 1944, is named for Marie and Pierre Curie. Marie Curie is the only person to have won a Nobel Prize in two fields of science. The point of this aside is to give an example of where physics and chemistry overlap. Radioactivity is a branch of physics. Marie Curie discovered the radioactive elements polonium and radium through chemistry. Marie Curie's work blurs the boundary between physics and chemistry. Back to the discussion of subatomic particles. Although their charges are exactly equal and opposite, a proton has 1,836 times the mass of an electron. A neutron has 1,839 times the mass of an electron. The reason why protons and neutrons are so much heavier than electrons is likely because electrons are simple particles, while protons and neutrons are composites of quarks. A proton is composed of 2 up quarks and 1 down quark. A neutron is 2 down quarks and an up quark. The quarks themselves have masses of only 4 to 10 times that of an electron. What makes protons and neutrons so heavy is the sum of quark kinetic energy and gluon binding energy that holds the quarks together to make the composite particle. From Einstein's famous equation E equals mc squared, we see that energy has a proportional mass. We could calculate the quantity of binding energy from the mass of the composite particle. Nearly 99.8% of the mass of protons and neutrons is the binding energy that holds their quarks together. Quark binding energy is a physics topic, not a chemistry topic. We are still left with the mystery of what is energy, just as we are left with the mystery what is charge. What we can say about electrical charge is that it is absolutely necessary for chemistry to exist. If the components of atoms did not have charge, atoms would not interact and there would be no chemical actions or reactions of any kind. I repeat, the essence of chemistry is electrical charge. And what is the result of charge? Two fundamental chemical actions: repulsion and chemical attraction. Repulsion causes pressure, prevents objects from passing through one another, or may cause hydrophobic effects, such as water beating on a surface or miscibility between two liquids. Chemical attraction results in bonding between substances. Bonding is what most people think of when they think of chemistry. They are correct. A lot of chemistry is about bonding. Before we can discuss repulsion and bonding, we need to discuss atoms in the periodic table of elements. Atoms are the building blocks of substances. Atoms are the smallest unit that contains all the properties of a pure substance or elemental material. An atom is composed of a nucleus and an electron cloud. The nucleus contains protons and neutrons. In a neutral atom, the number of electrons equals the number of protons in that atom. The neutrons are present to work with the strong nuclear force to keep the positively charged protons from repelling each other and blowing the whole nucleus apart. During chemical processes, atoms can gain or lose electrons. Atoms with an electron count that is different from their proton count are called ions. Atoms that have more electrons than protons are called negatively charged ions or just negative ions. Atoms with less electrons than protons are called positive ions. In chemistry processes, the number of protons or neutrons in an atom do not change. If an atom does gain or lose protons or neutrons, that would be a nuclear physical reaction, not a chemical reaction. To retain its status as a chemical element, an atom's proton count, or atomic number, always stays the same. In chemical processes, the elements are conserved. In chemical reactions, it is only the combinations of atomic elements that are rearranged. In chemistry, the electron arrangements change. The nuclei of the atoms remain unchanged. How and why chemical reactions occur can be best understood by understanding the layout of the periodic table. The periodic table of elements contains the elements laid out by period. Early chemists found that the behavior of elements repeat every 8 columns or is periodic. For example, every element in the first column is an alkali metal. Lithium has a similar behavior to sodium just beneath it. Likewise, every element in column 17 is a halogen gas, and all halogen gases behave similarly. Fluorine has a similar behavior to chlorine just beneath it in the same column. They are both highly reactive gases. An element contains one type of atom with a fixed number of protons. For example, the element oxygen always contains 8 protons. Add 1 proton to oxygen and one gets fluorine, which is a totally different element with a totally different behavior. Hydrogen is an element that contains 1 proton. Water is not an element. It is a molecular compound of 2 hydrogen atoms bonded to 1 oxygen atom. In chemistry script, water is H2O. If we look at the element boxes in the periodic table, every box contains the element's name, its symbol, its atomic number, and its atomic mass or standard atomic weight. Atomic number is the number of protons in the element. The atomic number is always an integer. The atomic numbers 1 through 92, hydrogen through uranium, are naturally occurring elements. The elements neptunium, plutonium, etc., or atomic numbers 93 and greater, are synthesized by scientists in a nuclear reactor and cannot be found in nature. The atomic mass has a strict definition for a particular isotope of the element. Different isotopes of an element have different numbers of neutrons. For example, common isotopes of copper are Cu-63 and Cu-65. Cu-63 has 29 protons and 34 neutrons. Cu-65 has 29 protons and 36 neutrons. The atomic mass of an atom is the mass of all its protons, plus the mass of all its neutrons, plus the mass of all its electrons, plus the mass of all the binding energy holding the atom together. The mass is displayed in atomic mass units, or AMUs. There is an error in the periodic table in the figure. It says atomic mass, but it really should say standard atomic weight. A standard atomic weight is the average of the atomic mass of each element isotope weighted by the fraction of the element's isotopes found on Earth. For example, on Earth, 69% of copper atoms are the Cu-63 isotope, and 31% of the copper atoms are the Cu-65 isotope. Including its binding energy, the Cu-63 isotope has an atomic mass of 62.9296 AMU. The Cu-65 isotope has an atomic mass of 64.9278 AMU. 0.69 times 62.9296 plus 0.31 times 64.9278 is about 63.546. A professional chemist would need to be more precise. For our purposes, we could get a good guess of the number of neutrons in the most common isotope of an element by subtracting the atomic number from the standard atomic weight listed in the periodic table and then rounding up or down. Again, a professional chemist would need to be more precise. Different fractions of isotopes in a rock might help us determine the region the rock was from, or even if the rock is a meteorite from outer space or from another planet where the isotope fractions would be different from that on Earth. We can identify meteorites that have been blasted off the surface of Mars and landed on the Earth by the difference of the isotope fractions from Earth rocks. In the periodic table, the rows stand for how many energy levels are available in the ground state, and the column tells us how many electrons fill the orbitals of that energy level. For example, in its ground state, magnesium Mg has 3 electron shells, and 2 electrons occupy the third energy shell of that element. The simple explanation of why elements in the same column behave similarly is because elements in the same column have the same number of valence electrons. Valence electrons are the electrons that give an element its chemical character. Electrons orbit the atomic nucleus in electron shells or energy levels. There are 4 different letters used to label the orbitals: S, P, D, and F. Valence electrons occupy the S or P-type orbitals of the outermost electron shell. The electron orbitals are believed to have different shapes. Electron orbits are not necessarily the circular or elliptical orbits the planets orbiting the Sun have. S orbitals are believed to be circular. P, D, and F-type electron orbitals are shaped more like figure eights or hourglasses, with the axis of the figure eights being at varying angles relative to each other to keep them separated. The electron orbitals are the shapes of the electron's wave modes. An analogy to electron orbital shapes might be the standing waves of a guitar string between its 2 bridges or end nodes. A node is a point where the wave stays at 0 amplitude. The guitar string must always oscillate in some integer multiple of the half wavelength between the 2 end nodes. At different harmonics of the guitar string, its wave equation must always be 0 at its end nodes. And the spacing of any nodes or zeros in between must be integer multiples of the half wavelengths of the fundamental frequency. Other modes or harmonics of a primary vibration are integer multiples of the half wavelength. The second harmonic mode has 3 nodes or 2 half wavelengths. The third harmonic mode has 4 nodes or 3 half-wavelengths. The fourth harmonic mode has 5 nodes or 4 half-wavelengths. The secondary harmonics are always integer multiples of the primary frequency. The spacings between nodes or 0 points are always equal to each other in that mode. Likewise, the wave shapes of the electron orbitals are the standing wave mode shapes of the electron's wavelength. The figures show the s, p, d, and f orbital shapes or modes of an electron's wavelength. The last figure is a real photograph of diatomic gas molecules, maybe O2 or N2, showing the real electron clouds around the atoms really are the shapes drawn in the previous figures. The electron shell is divided up into 7 energy levels. The first energy level, the energy level closest to the nucleus, has only one s-type electron orbital. The second energy level has both s and p-type orbitals, as does the third energy level. The fourth and fifth energy levels have s, p, and d-type orbitals. The sixth and seventh energy levels contain s, p, d, and f orbitals. In the ground state, or lowest energy state of its electron cloud, the electrons in hydrogen and helium atoms occupy only the 1s orbital. For helium, the 2 electrons in the 1s energy shell must spin in opposite directions to each other. Wolfgang Pauli gave us his famous Pauli exclusion principle, which says that no 2 fermions can have the same quantum number. The exclusion principle, as applied to electrons, means that if 2 electrons occupy the same electron orbital, they must have opposite spins. Since there are only 2 spin directions, one electron orbital can at most hold 2 oppositely spinning electrons. There is only one s-type orbital at each energy level. Energy level 1 has only an s-type orbital shell. Starting at energy level 2, there are 3 p-type energy shells at each energy level. Since each energy shell can hold 2 electrons that have opposite spins, that means that if all the s and p energy shells are filled in the outermost energy level, that means that the element has a total of 8 valence electrons or an octet of valence electrons. There is something special about having 8 valence electrons. An octet is the lowest energy state that an electron cloud can be in. We do not know why that is true. So far, only God knows why. But we do know what it means for chemistry. If an atom has an octet of valence electrons, it is electronically satisfied. It is in its lowest energy state. The atom no longer participates in chemical reactions. Writers, including myself, often misuse words like satisfied, wants, willingly, and needs that give the false impression that inanimate objects like electrons, atoms, or collections of atoms, like a rock, has a mind, a will, and need and wants that can be satisfied or made happy. It is a shortcoming of human language that everything is humanized to make its behavior easier to understand. English lacks the proper words to describe inanimate behaviors in straightforward terms. If humanized terms are to be avoided, it usually takes a long roundabout route to describe the behavior of inanimate objects like electrons or atoms or collections of atoms like a rock. Electrons, atoms, rocks, or any other collection of atoms have no mind or will of their own. Inanimate objects simply obey the laws of physics. The simplest thing we can say about inanimate objects is they always take the path of least resistance to a state of lower energy. Nature seeks the lowest energy state. Again, the word seeks implies a mind with desires. Such words are difficult to avoid when discussing the behavior of objects with no mind and no desires without a long, complicated analogy. We can try to avoid humanizing or anthropomorphizing the behavior of inanimate objects by talking in terms of energy. We can draw an analogy to a ball at the top of a hill. At the top of the hill, the ball has high potential energy. If it rolls to the bottom of the hill, the ball is in a lower energy state. The ball will lay at the bottom of the hill indefinitely unless an outside force causes the ball to move. Likewise, an atom with an octet of electrons in its s and p orbitals has a lower energy state than in any other electron configuration. The atom will not change its octet state unless forced to change by an external energy source. If we look at the last column of the periodic table, column 18, we see all the noble gases, from helium to radon. The elements in this column are noble gases, noble because they are always found in pure form. The noble gas atoms don't bond with the common elements, or even to each other. They are satisfied remaining unbonded because their valence electron shells are full. The S shell of helium has its full complement of 2 electrons. Neon through radon contain both s and p-type orbitals in their highest energy levels. All 8 of their s and p orbitals are filled, so they are satisfied. These gases do not participate in chemical reactions, and so are noble gases. All other common elements bond with other elements to get their top level s and p orbitals filled by sharing electrons with whatever atom they have bonded with. All other elements are trying to get in the same full octet state of the noble gases. For example, sodium, Na, wants to lose 1 electron to attain the same electron octet state as the noble gas neon, Ne. Chlorine, Cl, wants to gain 1 electron to fill its s and p shells to get the same electron octet as the noble gas argon, Ar. The bond of sodium with chlorine results in the molecule NaCl, sodium chloride, or ordinary table salt. If you notice, the periodic table of elements for the first 3 energy levels have only s and p type electron orbitals. By the 4th row, which represents the elements that have electrons in 4 energy levels, there are 10 elements in the gaps columns. Scandium, Sc through zinc, Zn. The elements at energy level 3 and greater have d-type orbitals in addition to s and p-type orbitals. Note, the 4s orbitals will fill before the 3d orbitals. At energy level 6 and 7, the elements have f-type orbitals in addition to sp and d-type orbitals. At energy level 6, most periodic tables break out the elements with f-type orbitals in a separate subrow called the lanthanide series, lanthanum through lutetium. At energy level 7, there's a subrow for the actinide series, actinium Ac through lawrencium Lr. Some scientists argue that the lanthanide series should start with cerium Ce and the actinide series should start with thorium Th. They are correct in that there should be an even number, or 14 elements in each series. Not the 15 elements shown, as the f orbital electrons occur in 7 opposite spin pairs. Elements with 6 or 7 electron shells have 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. Each orbital can, at most, hold 1 pair of electrons of opposing spin. Only God knows why the electron shells have this configuration. But it is interesting that scientists have found that there is order to the electron clouds surrounding the nuclei of atoms. In a single atom, the electrons orbit the nucleus of protons and neutrons in distinct orbitals or electron shells of varying energy. According to the Pauli exclusion principle, only 2 electrons can orbit in the same electron orbital, and these electrons must spin in opposite directions to one another. The electrons fill the electron shells closest to the nucleus first, and so in its ground state, the atom is in its lowest possible energy state. To cause an electron to move to a higher energy level, it requires the addition of energy. When electrons are in higher energy levels than the ground state, the atom is said to be in an excited state. Within a very short period of time, the excited electron will drop back into lower energy levels towards its ground state. In doing so, it will release a quantum of energy it absorbed in the form of a photon with the exact same energy as the energy difference between the energy levels that it jumped between. In quantum physics, the jump between energy levels takes zero time. The electron disappears at the higher energy level and simultaneously reappears at the lower energy level. The photon is released instantaneously. This release of photons is why hot materials glow. They are releasing photons as they cool or lose energy. For a given atom, the energy difference between like energy levels is always the same. Scientists can determine the type of atom that is excited by the color of the photon. Bluer photons have higher energies than redder photons. And every element has its own spectrum at which it absorbs or releases electrons. Einstein received his one and only Nobel Prize for describing this photoelectric effect. Einstein correctly explained the photoelectric effect in a paper he wrote in 1905. The Nobel Committee did not grant him the Nobel Prize in Physics for the photoelectric effect until 1921. Einstein never won a Nobel Prize for his most famous work in special and general relativity. The Russian chemist Dmitry Mendeleev is credited with developing the first usable periodic table during the 1869 to 1871 time period. Prior to Mendeleev, the German chemist Lothar Meyer published a rudimentary periodic table in 1864, and the British chemist John Newlands published a rudimentary periodic table in 1866. In 1882, the Royal Society in London awarded the Davy Medal to both Mendeleev and Meyer for their work to classify the elements. In 1871, there were only 63 known elements. What made Mendeleev's table useful is that he left gaps in his periodic table where he predicted other elements would be found. Mendeleev's gaps prompted other scientists to search for the missing elements. About half of Mendeleev's gaps did predict real missing elements that were discovered in the decades that succeeded the publishing of Mendeleev's 1871 periodic table. The modern periodic table contains all the naturally occurring elements up to element 92 uranium and the man-made elements well into the 110s. And that concludes my introduction to chemistry and the periodic table of elements. In my next video, I will focus on chemical bonding. Thank you for watching. If you enjoyed my video and would like to help me make similar content, please hit like and subscribe.